The strange part of max flow is that the algorithm sometimes improves by going backward. That backward edge is not a bug, it is how earlier choices get repaired. The network is teaching humility, capacity, not intention, controls movement. By the end, you should be able to trace one unit of flow, find the bottleneck, use a residual edge to repair a bad early push, and read a cut as the proof receipt. An edge capacity is the most flow that pipe can carry. Sending more than capacity violates the problem. The bottleneck question is where the smallest spare capacity sits, because that one pipe controls the whole push. The source produces flow. The sink receives flow. Every other node is a junction that must pass along what comes in. The source injects flow and the sink absorbs it, while middle nodes must pass along what they receive. At intermediate nodes, flow in should equal flow out. The node is not allowed to create or destroy flow. Conservation is bookkeeping. At a middle junction, incoming flow must balance outgoing flow. The value of a flow is how much leaves the source, or equivalently how much enters the sink. That is the number we try to maximize. Flow value counts what leaves the source, which is also what successfully reaches the sink. Pause at the junction. Does incoming flow equal outgoing flow? A flow network has three rules: never exceed pipe capacity, conserve flow at middle nodes, and measure what leaves the source or reaches the sink. Those rules keep the pipe metaphor honest. The network is teaching humility, capacity, not intention, controls movement. An augmenting path is a route from source to sink that still has leftover capacity. If one exists, the current flow can improve. The bottleneck question is where the smallest spare capacity sits, because that one pipe controls the whole push. The bottleneck is the smallest remaining capacity on an augmenting path. It decides how much extra flow can be pushed safely. The smallest spare capacity on the chosen path sets the size of the whole push. The bottleneck is the uncomfortable truth in the system. Everything else may look generous, but the narrowest edge sets the push. Residual capacity means how much more can be sent forward, or how much previous flow can be undone backward. The receipt has two numbers at once: forward spare capacity and backward undue capacity. The backward edge means, we are allowed to undo part of a previous decision if rerouting creates more total flow. A backward residual edge does not mean physical flow travels backward. It means the algorithm can cancel part of an earlier decision, free that capacity, and reroute it through a better path. Repair story: one early push blocks the better arrangement. The backward residual edge gives the algorithm permission to revise without starting over. Backward edges feel unnatural until you see the psychology. Good systems need permission to revise earlier choices. Ford-Fulkerson repeats a simple move: find an augmenting path, push the bottleneck amount, update residual capacities, and look again. The bottleneck question is where the smallest spare capacity sits, because that one pipe controls the whole push. Before the next push, predict the bottleneck: which spare capacity is smallest. The network is teaching humility, capacity, not intention, controls movement. Edmonds-Karp is a specific version that uses BFS to choose augmenting paths. That makes the behavior more predictable and easier to analyze. An augmenting path is a legal improvement route through the residual network. The amount you can push is not the sum of capacities, it is the smallest spare capacity along that path. A cut separates the source side from the sink side. For max flow, count only directed capacity going from the source side toward the sink side, that is the pipe wall flow must cross. A cut is a wall between source and sink. The outgoing capacity of that wall limits all possible flow. The cut is not decoration. It is the moment the network says, this is all I can possibly carry. The max flow min-cut theorem says the maximum possible flow equals the directed capacity of the minimum source to sink cut. Bottlenecks are not just symptoms, they certify optimality. Max flow min-cut is the receipt: once the reachable side cannot cross more capacity, no hidden augmenting path remains. When no augmenting path remains, the residual graph itself proves that the current flow cannot be improved. The bottleneck question is where the smallest spare capacity sits, because that one pipe controls the whole push. Bipartite matching can become a flow problem, source to left nodes, left to right edges, right nodes to sink, each match carrying one unit. In matching, capacity 1 turns each chosen pair into one unit of flow and prevents double booking. When the reverse arrow appears, read it as permission to undo part of an earlier choice. The network is teaching humility, capacity, not intention, controls movement. Some scheduling and assignment problems also become flow networks. The trick is turning constraints into capacities. With integer capacities, classic augmenting path methods can produce integer flows. That is why matching comes out as whole pairings, not fractions. A route may look open, but if a middle junction already has incoming and outgoing constraints, conservation matters. The bottleneck question is where the smallest spare capacity sits, because that one pipe controls the whole push. The backward edge is the surprising part. It does not mean water literally flows backward. It means the algorithm is allowed to cancel part of an earlier choice so a better overall routing can happen. For example, push 3 units through a tempting pipe, discover 1 unit blocks a better crossing, send 1 unit back in the residual graph, and reroute that unit through the spare pipe. The total rises because the earlier choice became editable. The network is teaching humility, capacity, not intention, controls movement. Without backward residual edges, the algorithm cannot recover from earlier choices. Residual graphs are the difference between greedy pushing and real flow reasoning. The network is teaching humility, capacity, not intention, controls movement. Flow is not asking for the shortest route. It asks for total transferable amount under capacities. Repair checkpoint: if one early push blocks the network, which residual edge lets the algorithm revise it? The network is teaching humility, capacity, not intention, controls movement. The cost depends on how augmenting paths are chosen and how many times they are needed. Algorithm choice matters a lot at scale. Nuance: Ford-Fulkerson depends on which augmenting paths you choose. Edmonds-Karp uses BFS to make the bound predictable. Ask: what is the source, what is the sink, what limits each edge, what must be conserved, and what cut would prove the answer? The bottleneck question is where the smallest spare capacity sits, because that one pipe controls the whole push. Push 3 units through one path, create a backward residual edge, undo 1 unit, reroute it through a better pipe, then inspect the source-to-sink cut that proves no more flow fits. Trace one augmenting path, find the smallest spare capacity on the path, push that much flow, then update both forward and backward residual capacity. The network is teaching humility, capacity, not intention, controls movement. After the last augmenting path disappears, draw the reachable source side in the residual graph. The outgoing capacity of that boundary is the certificate that the current flow is already maximum. The reachable side of the final residual graph gives the receipt for why the current flow is maximum. For bipartite matching, each chosen pair carries 1 unit of flow. Capacity 1 prevents a person or job from being matched twice, so a flow value becomes a matching size. A flow value becomes a matching size when every used left-to-right edge represents one chosen pair. Before declaring victory, draw the final cut and ask whether any source-to-sink path still survives. The max flow min-cut theorem gives the final certificate. If every source-to-sink route crosses a full cut, no algorithm can push more flow. The bottleneck is no longer a guess, it is a proof. The network is teaching humility, capacity, not intention, controls movement. If you only push along the first open pipe, an early choice can block a better later arrangement. Residual edges are the repair mechanism that turns naive pushing into an algorithm. A max flow answer is usually a collection of many paths sharing capacity. The total value can increase even when no single path looks impressive by itself. Network flow is pressure through a constrained system. Augmenting paths add pressure, residual edges preserve flexibility, cuts reveal the bottleneck. That is why flow is useful beyond pipes. Matching workers to jobs, routing packets, and assigning resources all become the same question: what can move through this network without violating capacity? Flow uses capacities, conservation, augmenting paths, residual graphs, and cuts. Max flow is not just a number, a minimum cut can prove it is the best possible. Next, we will study NP completeness, the wall that appears when efficient algorithms may not exist. The network is teaching humility, capacity, not intention,